Let's begin. So today is the last session on conventional machine learning, and we conclude this topic with classical reinforcement learning. And I would argue that classical reinforcement learning is even more primitive than conventional machine learning. As you will see, you don't even use functional approximators such as linear models or support vector machines. The structure we'll use is just a good old table of values, and that's why we use the word tabular for these methods. And I'll talk about them in more detail today. And in this session, we build basically the foundation of more advanced methods, such as approximate reinforcement learning, and then later deep reinforcement learning, which we're going to discuss in week 12. Here's our plan for today. We start with some introductory material on the meaning of machine learning and its different categories, and continue with some kind of philosophical positions and remarks on the nature of mind, and the meaning of intelligence, and the biological hypothesis on the purpose of having a brain and things like that. Then we skim through some reinforcement learning achievements, their history and concepts such as Multiarmed Bandit, to understand notions such as exploration and exploitation better. And then we also introduce the mathematical framework to formulate a reinforcement learning problem, which is Markup decision process. And then finally, we propose 3 classical reinforcement learning algorithms to solve reinforcement learning problems. And then in the practical, we will have a chance to implement all 3 of them for 2 block world environments, the windy grid world and the OpenAI Jim's taxi environment. So let's talk about the big picture of machine learning. So what are the essential differences between machine learning algorithms and the one that we studied in the algorithm courses? I always had this question that what is really the difference, the essential difference between analytical algorithms as we discuss them in our data structure and algorithm courses and machine learning algorithms. And I kind of realized that you can kind of divide them based on the way they behave and the way they change themselves and they influence the data. So in analytical algorithms, they work like filters and catalyzers for the data, and they're generally built to process and change the data. But in machine learning algorithms, so they work like digestive systems. The goal is to change or to improve the algorithm using the data. And then once the kind of digestion or training is over, then machine learning algorithms can act like an analytical one. Well, unless the training is online and continuous. And the other thing is that in the analytical one, data does not change the structure or behavior of the algorithm, whereas that's the whole gist of machine learning. And the other thing is that, for instance, in analytical one, if you sort a million arrays with a bubble sort, you're not going to make it a quick sort. But in machine learning, that's the case. The algorithm changes itself and improves itself. And in the classical and tabular reinforcement learning, which is our topic today, that the changing data structure is a table of values, and in approximate and deep RL, it's a linear model or a neural network. So I think you all saw this big picture of machine learning and their differences. That we have 3 main classes of machine learning: supervised learning, unsupervised learning, and reinforcement learning. But I thought I'd look at it from a different perspective and the goal of these different branches of machine learning. So the main thing about supervised learning is that it's there to generalize. And you saw that in classification and regression, you can just basically draw a line and divide your data in different sections. And that's a generalization. You basically sum up things and simplify things. In supervised learning, in unsupervised learning, which we haven't covered yet, so I think you'll see some of it in the second part of this course. We don't have any label data. The goal is to compress, and a good example of that is clustering and the dimensionality reduction. So, you know, in conventional machine learning, we have k-means and PCA for dimensionality reduction. But also in deep learning, we also have variational autoencoders that are considered as unsupervised learning methods, and they're usually used to reduce the dimensionality of data and make it easier for the classifier or the supervised learning part to categorize it. And then, so reinforcement learning, the goal of reinforcement learning is to act. We're here to create agents that are capable of doing things in the world or in certain environments. They're not necessarily part of the real world, the physical world, but they can be part of a kind of virtual world, a game, or I don't know, maybe your agent is living in the world of stocks and selling and buying stocks, and the goal is to enhance and increase your profit. And so by combining kind of these three, you can also come up with some novel things. So for instance, deep reinforcement learning here, in deep reinforcement learning or approximate reinforcement learning, you basically combine the generalization power of supervised learning and acting powers of reinforcement learning. And so by deep learning, which is kind of a buzzword, it's basically a better or stronger method for supervised learning. Not always, but in most cases, because of its modularity and the fact that you can make it larger and larger, it's just stronger compared to other conventional methods of supervised learning. And the other thing is imitation learning. We may touch on imitation learning on week 12. It's basically using data sets of experts' behaviors and a supervised learning type algorithm to learn how to act. I think the history of imitation learning is, it dates back to 1980s when Alvin was developed, and it could successfully drive from coast to coast of the United States, and it was basically trained by an imitation learning algorithm. It's usually a kind of complementary method to reinforcement learning algorithms. All right, so let's talk about mind, brain, and intelligence. So this slide is about philosophy. I'm going to philosophize a little bit here. So before going any further, let me explain why I included this slide. I was a little skeptical of doing this because it's really not directly relevant. But I observed that a lot of confusions about AI and its branches originates in a misunderstanding about its nature and the conceptual level. And I thought maybe this helps some of you to relate better to the notion of mind. And remember that, so in many cases, we confuse life, mind, consciousness, and self-consciousness. These are different things. And so we humans just happen to have all of them, but that's usually, another source of confusion. For instance, a lot of fears from, artificial intelligence or intelligence itself, it has nothing to do with intelligence at all. It's one of the problems of life. And so living things they tend to grab onto resources and try to keep it for very obvious reasons because of the pressures of life. And intelligence might be a tool for them, but it has nothing to do with intelligence itself. So what do we mean by philosophy here? Because these are basically different theories of philosophy of mind. Because sometimes when I say this is my philosophy, I mean I believe in this thing. But in this context, my philosophy, and at least from an analytical tradition perspective, simply means that the ability to uncover and capture ideas, concepts, and arguments, most importantly, on a specific topic and weigh and discuss them. And in other words, to kind of meditate or contemplate on the knowledge that's available. And the goal isn't exactly discovering truth, but because that's usually the role of the scientist, but the ultimate level of clarity on what we think as truth. And because in many cases we think we know what we know, but upon reflection we discover how little we knew. And so given that, let's talk about the philosophy of mind. So philosophy of mind is a kind of superset of many branches of knowledge, from beliefs in theology and religions to psychology, neuroscience, and artificial intelligence. And as you can see in the figure, we can divide different theories of mind into two main categories: dualism and monism. Dualism divides our kind of existence into two substances, body stuff and mind stuff. It dates back to to ancient times, but Descartes argued for these positions. So for instance, if someone believes in soul, spirit, afterlife, or a supernatural part of the mind, they kind of belong to dualism school of thought, or at least borrowed elements from it. And dualism has two subdivisions, substance and property dualism, which I'm not going to discuss here, but substance dualism is more, so yeah, this guy is more similar to the religious idea of a soul, and property dualism is a modern invention proposed by the Australian philosopher David Chalmers, who you can see his book at the bottom of the page. You can read it as a reference if you're interested. Monism, on the other hand, so this part of the picture, considers only one true substance. So if you believe that only mind exists and the world is just a simulation in your mind, something like Matrix or something, then you're an idealist. And if you believe that the world exists and mind is a construction out of matter, then you're a materialist. And it doesn't need to mention that almost all scientific community is sitting on this side of the picture. There are a lot of stuff here which we don't have enough time to cover, but we cover the most popular ones very briefly. And so one of them is identity theory, and the identity theory asserts that the mind and the brain are the same thing. And another very close school of thought that is connectionism, and that defends this position that mind is just emergent phenomenon as a result of neural activity. And obviously it's very close to neuroscience and neural networks, biological or artificial. The other thing is behaviorism. So behaviorism doesn't care much about the essence of mind, but suggests that we need to investigate the behavior to understand the underlying mechanism. And not surprisingly, it's a methodology because of its kind of practical approach in psychological research, and very close to reinforcement learning. In fact, many behaviorists led to theories of reinforcement learning in psychology. And finally, functionalism is promoting the idea that mind is a function, no matter how you implement it. So for instance, it doesn't matter if I use certain protein in human mind or brain to do it, or in octopus, which has radically different things, but it has the same function. And so in machine learning and deep learning, we also tend to reduce everything to a function with inputs and outputs. And that's very, very aligned with this position. So how would I define mind? Firstly, I should say that I don't know. I mean, all of these scientists and philosophers are still struggling to find it, and it is still an open question. But if I am kind of cornered, I have to provide a definition that's aligned with AI and reinforcement learning. I would say that mind is an entity capable of acquiring a representation of its environment, and that representation is not passive, but it's actively serving a function, such as guiding actions of an agent or an organism in its environment. All right, enough of philosophizing. So what is intelligence then, and why do we need brain for it? We can define it in different ways, but in a certain sense, intelligence is like sugar. It doesn't really exist in a pure form in nature. We have intelligent behavior by kind of animals or humans, and we kind of abstracted it out of nature and we call it something. But simply, intelligence can be defined as a cognitive part of action, and clearly the common denominator of all intelligent activity includes efficient information processing and storage, which leads to very good decision making. And neural networks are really good for this, biological or artificial, because of their properties. They're parallel, modular, and multi-purpose. And of course, they're aligned with multi-cellular nature of life. And notice that the current state of deep learning and neural networks has very little to do with its biological counterpart. It was inspired by biological neural networks, but in many cases, it's kind of diverging to other directions, as you will see in the second part of this course. Now, a hypothesis, if you look at nature, so let me first assert this. The hypothesis is that brains, decision-making and motor function co-evolve. And decision-making is usually regulated by this extremely expensive organ, the brain, or kind of some sort of central nervous system. Sometimes it's ganglia in kind of smaller creatures. A good example that can support this hypothesis is C-squared. And this is basically the lifespan of a C-squared. It's born with a small brain, one eye, and a small tail. And when it's born, it looks around and finds a solid rock to settle down. Once it finds it, it kind of attacks it to it permanently, digests its tail, eye, and brain, and sits there for the rest of its life. And you know that evolution hates redundancy, so it's the kind of a use it or lose it idea. And this kind of supports this hypothesis of close relation between brain decision-making and motor functions. At least that's how neuroscientists viewed this. And if you can see look at the nature, trees don't have brains, and so nervous system central like us, or distributed like jellyfish, only happen to those who need to do things such as swimming, attacking, finding, escaping, or finding resources, and so on. So after that, let's talk about different ways of creating intelligence. So you already know that in analytical algorithms, we talk about them, they can program it, right? So it's not necessarily programmed in Python or C, but it can be genetically programmed in, for instance, biological processes like such as digesting your food or growing hair. These are the things that we do, but we don't know how, and they're programmed by our genes. But anyway, these are static. These are pretty much static. Or so the motto is that give a man a fish and he will eat for a day. Or you can teach it like supervised learning. Teach a man a fish to fish and he will eat for a lifetime, such as supervised learning and or imitation learning among animals. Or you can provide the motivation, or give a man a taste for fish, he will figure out how to get fish even if the details are changed. And so one of the reasons I kind of added these photos is that these two agents learn how to play these things, and one of them learned how to run. And you can see how awkward they're running and moving around. And the reason is that they have no role models for their action. They just learn from scratch. And that's kind of the details change that was mentioned. So what is exactly reinforcement learning? Reinforcement learning is basically a computational approach to learning from interaction. So again, what makes reinforcement learning different is that there are no supervisors, only reward and feedback signal, or the equivalent of pain and pleasure in nature. We have delayed feedback, so you do something and you will get the feedback much later. The sequence of decision matters. So what you do now will influence what you're going to perceive tomorrow and what you're going to do tomorrow, and so on and so forth. And the current decision and actions influence later states and data we receive. So as a result, reinforcement learning provides the formalism for intelligent and adaptive behavior. So as you can see in this diagram, for instance, the agent does something, environment generates the new state and a new reward, and this loop continues. It's also called the MVP loop. You can see this kind of pattern in kind of classical conditioning in psychology. And you can also use neural networks for this, which I think this image is more appropriate for week 12. Right, so that was a very quick and fast introduction to reinforcement learning and intelligence itself. Let's talk about the history of reinforcement learning and its achievements. So everything kind of started in 1959 by Arthur Samuels. We can trace even the roots of reinforcement learning to Arthur Samuels' checkers player. So he believed that teaching computers to play games was very fruitful for developing tactics appropriate to general problems, and he chose checkers as it's relatively simple, though has a very deep depth of strategy. So the main driver of the machine was a search tree of the board positions reachable from the current state. Since he had only a very limited amount of available computer memory, Samuel implemented what is now called alpha-beta pruning. And instead of searching each path until it came to the game's conclusion, Samuel developed a scoring function based on the position of the board at any given time. And this function tried to measure the chance of winning for each side of the given position. And these ideas later manifested as the reward and the value function in reinforcement learning literature. Then we have Gerald Tesoro in late 1980s and early 1990s. He developed his TD gammon, which was an intelligent agent using reinforcement learning algorithms, TD lambda, basically, and that's why it was called TD gammon. And it was one of the most first successful examples of combination of reinforcement learning and multi-layer neural networks. And the notion of self-play also introduced. It wasn't introduced, but it was kind of applied here. And it was also using later approaches such as AlphaGo and AlphaGo Zero in 2015 and 2017. And so the thing is, after 6 weeks of training, so I think maybe it's a kind of an apocryphal tale, but as the story goes, or legend has it, that after 6 weeks of training, it became so good that even the grandmasters of backgammon couldn't beat it, and that was kind of the story of TD gammon. Then we have so there's a 20 years gap between TD gammon and the next kind of breakthrough, the Atari games, the DQN paper, and most of it's not really any theoretical shortcoming, but mostly resources. So from 1990s, we had an explosion of computational power, and that led to the DQN paper and the DQN from DeepMind. And they kind of basically raw their agents how to play games from pixels, and there was no handcrafted features here. And they also later used recurrent neural networks to capture temporal patterns, but it kind of ignited an explosion of papers and state of the art after that. Then, of course, the most popular one, the AlphaGo Zero. So just one thing, we're gonna implement a DQN on week 12 for some classical control problems. AlphaGo Zero was very popular. We'll talk about it. I don't think we have time to implement this on week 12, but they used a combination of convolutional neural networks and Monte Carlo tree search for kind of doing this. And as you know, they beat the grandmaster of Go in 2017, I guess. And a newer achievement was Dota 2 in 2017 and StarCraft. So one by OpenAI, the other one by DeepMind. And I think in both, these are multiplayer games. And so on one side, we had artificial reinforcement learning agents, and the other side were grandmasters, human grandmaster team. And I think in both cases, the reinforcement learning agent won. But you should know the gigantic amount of resources they consume to train these agents. I heard somewhere that they kind of trained their agents for the equivalent of 10,000 years of human time. So if we were supposed to train that amount, we had to spend 10,000 years to train that much. Anyway, these are kind of game-based, board game-based, but we also have some stuff in robotics. So these are early works. So you can see that this is from 1990s, and the one on the bottom left is a bit creepy, but it looks like a severed hand of a zombie. But little by little, it learns how to crawl, and eventually it kind of managed to do that. And the other one learned how to crawl in a kind of lizard way. And these are kind of early works of robotics and a combination of robotics and reinforcement learning. And then there are newer works. This is from 2015, I guess, training a bipedal robot to walk. Just by using pure reinforcement learning. It is used in self-driving cars. And in many cases, we develop controllers such as smart thermostats and adaptive air conditioning, autopilot systems. And so, for instance, in this case, I think this is from Stanford, they taught this agent to fly in reverse, which is extremely difficult to do. Because it has to deal with a lot of instability in kind of reverse flying, but the agent eventually learned how to do that. Right, so historically, the reinforcement learning has two main threads, both long and rich. They were pursued independently before intertwining in modern reinforcement learning. One thread concerns learning by trial and error and started in psychology of animal learning. So you know that we trained wild animals in circus for millennia, and that was basically based on reinforcement learning. And this thread runs through some of the earliest work in artificial intelligence and led to the revival of reinforcement learning early 1980s by Harry Clough, who wrote the book The Hedonistic Neuron. And the other thread concerns the problem of optimal control and its solution using value functions and dynamic programming. So you know that there's a kind of larger area in control engineering. It's called classical control or control theory, that you basically did study the physics or the dynamics of an environment, and then you develop basically design controllers to stabilize or guide something. But we have also this optimal control theory, which is basically a branch of mathematical optimization, and it deals with finding a control for a dynamical system, such as a spacecraft. And it's supposed to, I don't know, maybe land that spacecraft on a moon or something while minimizing its fuel expenditure. So reinforcement learning in general is a multidisciplinary topic. There are a lot of branches of science involved, and they're all providing material for reinforcement learning. They're also benefiting from its development, as you can see from this figure. Now let's talk about the theory of reinforcement learning. So there are three main elements in all reinforcement learning problems. We also have a biological equivalent of these. It's basically reward, state, and action. So a reward is a scalar. Usually, when you're dealing with reinforcement learning for artificial agents, it's usually a scalar feedback signal like +1 or 0, 1. We'll see more of this later. Or the equivalent of reward and punishment. It describes how well the agent is doing at that particular step or till that particular step. And humans also experience it as pleasure or pain, regulated by two things, at least: dopamine neurotransmitter, and there's this amazing brain structure called basal ganglia. So this is an image of chemical dopamine, and the basal ganglia is around here. It's on top of the brainstem. So the brainstem is basically a controller. They're kind of regulating things such as your blood pressure and things like that. But basal ganglia and substructures around here, such as amygdala. So, for instance, amygdala is in charge of processing fear, and fear is a very important factor in learning, of course. And basal ganglia is regulating your emotions and the way you walk and things like that, your motor functions. And they're also based on these rewards and punishments that you're receiving from our environments. The other thing, so that was reward. The other thing is a state or observation or percept is a vector, at least in reinforcement learning, is a vector that represents the state of the world that the agent inhibits. So it can be a numerical vector. It can be an image. So notice that an image itself is just a matrix, as you witnessed in your first assignment. So there are multiple, they can be also multiple vectors, and it's highly tightly related to sensors and robots and living organisms, such as our eyes and all of our senses. And then we have actions. Of course, after receiving the state and deciding what to do, the agent has to do something, and it's basically an outward signal from the agent to the world. And it helps the agent to modify the world for its benefit. For instance, the left to right movement in Atari games can be kind of different types of actions. And yeah. So let's talk about the reward hypothesis. In reinforcement learning, agents' goal is to maximize the cumulative reward, so like collecting a lot of good jobs, right? So the agent's goal is to maximize its total goal, not necessarily the most immediate one, right? And so as a result, reinforcement learning is based on something that is called reward hypothesis. And the thing is, we're saying in the reward hypothesis that all goals can be formulated by maximizing the expected cumulative reward. It might not be the case in some situations, but that's how we define it, and that we're kind of assuming. And the other kind of minor thing is that we consider rewards as a reliable source of guidance. And unfortunately, poorly designed reward systems can lead to the agent, they can mislead the agent, or they can be exploited. Well, a good example of that among humans is drugs and things that are kind of pleasurable, but they're really not rewarding in long term. These are also exploits and kind of flaws with reward systems. So some examples of rewards in designing agents. So in the game of Go, winning the game has the reward of +1 at the end of the game, and -1 when you lose it, right? Or in developing an autopilot system, when you're kind of perfectly following the predefined path, you will receive a +1. If you're causing any turbulence, you're going to receive -0.2. Any detour will give you a -1. And if you crash, there's a huge negative reward of -10. So I'm kind of assuming in such a setting, an agent learns little by little how to stabilize the airplane. So the other thing is building an air conditioning system. We have the same logic. Or balancing a cart pull, which is going to be our topic on week 12. Keeping the balance is +1. If it fails, rewards will stop, right? So stopping when the agent stops receiving those rewards, it's a negative thing. So the agent wants to continue to do that, and as a result, it learns how to stabilize it, like as you can see in the image. So we have the sequential decision-making problem, and it's kind of larger than reinforcement learning. But the goal is to select actions that maximize our total future reward. Again, not necessarily the immediate one. And we have these main difficulties whenever you're dealing with the sequential decision-making. So again, I think we're kind of reiterating some of these. So actions have long-term consequences. And you can also investigate these in your own life. This is really not the problem of reinforcement learning, it's the problem of our lives as well. There are delayed rewards, right? And when you receive them, you don't know which action was kind of in charge of that positive or negative reward. And there's this confusion about credit assignment, and it's called the credit assignment problem. It might be better to sacrifice immediate rewards to gain more long-term rewards. That's another problem, because you don't know how much and how many you should sacrifice and what's really reasonable in that particular context. This is something that an agent should figure out. And the other thing is exploration and exploitation dilemma, which I'll talk about in detail later. But that's another huge problem. Some examples, education, a very good example of that. It is really not fun to attend classes like this and listen and concentrate. It's really hard on your nervous system and all of that. And it may take years to finish and find a job, but eventually you will get to a state that you can enjoy what you got. And so that's one example. The financial investment, it may take months to mature, and in that process you may even lose money. So that's another thing. The other probably game-related one is facing an enemy in a video game. You may hit, get injured, or receive a negative reward. But again, to finish the game, you have to do that to kind of get the best prize in the game. And you can also think about kind of similar situations and identify these problems in them as well. So what is this exploration and versus exploitation dilemma? Exploration and exploration dilemma is a fundamental problem that any form of intelligence has to deal with. Even in evolution and evolutionary algorithms, we have to address it, which, as you know, happens by mutation. So exploitation simply means that you have an understanding of something, or you have some guess, and you make the best decision given the current information you have, right? And exploration is that you may realize that you may want to gather more information before making any further decisions. And so as you know, our goal is to find the best long-term strategy, which involves short-term sacrifices, which requires gathering enough information. And so these are some examples of exploration versus exploitation. So the thing is, without having enough information, it is really not possible to make a very, the optimal decision. But at the same time, you can't really starve yourself to death. So you must find the right balance. So in games, for instance, when you play, the move you believe is the best is exploiting what you know, and play an experimental move can be an exploration. It may lead to very bad results, but in the process, you may get some understanding about your environment. Again, we have the same thing in mutation. In mutation, mutation can lead to cancer, or it can lead to a biological breakthrough that help your species to move to the other level and solve some very serious biological problems. Or in personal life, it might be a little cheesy, but exploitation is continue dating your partner. Exploration is to date a new person. Again, the same problems apply to this situation. A restaurant, you can choose, you can go to your favorite restaurant or try a new one, which again can lead to very bad results, but that's the way you may eventually find the optimal one for you. So to solve the exploration dilemma, you know that in mathematics, we are still dealing with this and we still don't know how to deal with this, but there are at least three major ways that we can deal with it in reinforcement learning. So all those three are random exploration, optimization in the face of uncertainty, and information state space. So in random exploration, it's basically naive exploration. We have three subclasses. The one that we're gonna focus on today is the epsilon greedy. It's basically saying that add noise to a greedy policy. So it says that act randomly with epsilon probability, and it's usually small, or normally we may start from large values, but then finally we reduce that to smaller values. So we randomly choose stuff with 10% of the times, but in 90% we act greedily. We choose the best one. And the other thing, the other two are part of our week 12. One of them is softmax or Boltzmann exploration, so forming a probability distribution over action space and sample from it. And of course, it is weighted by the probability of our actions, so the optimal action has a higher chance of being chosen, but others are also not missing out. In a way, it's more intelligent than epsilon greedy, because other actions are also proportional. Other actions will be chosen proportional to their probabilities, and they're not static like epsilon greedy. And the third solution is Gaussian noise, simply adding noise to the normal distribution to each action. Again, this is something that we're going to consider on week 12. Optimism in the face of uncertainty is kind of interesting. It also encourages, that optimism is encouraging exploration. So we set the initial values of something to a high value, and the algorithm tries a lot of things before settling on a value. And I guess I don't know how is it related or not, but I think to me a good analogy for this is little kids and toddlers before learning what a horrible place the world can be. They're trusting and not fearful, which has a lot of learning values, and so this encourages their exploration as well. The other thing is information space. We considered information from look-ahead search to help the reward, given indices and Bayes adaptive Markup decision process. They're really not that helpful in reinforcement learning. We mostly use the random methods in our exploration policies. All right. The multi-armed bandit is a kind of miniature environment and platform that can demonstrate how exploration and exploitation works. So by expanding this, we can address real environment in reinforcement learning as well. What is a multi-armed bandit problem exactly? So you know that a bandit is someone who steals your money, and so it basically means thief. You know, in casinos, a one-armed bandit is a simple slot machine where you insert a coin into the machine and pull a lever, and you get an immediate reward. But why is it called bandit? Well, it turns out that all casinos configure these slot machines so that all gamblers end up losing money, and hence the name. Now, a multi-armed bandit is a complicated slot machine. It's like as if you're stacking all these slot machines, and there are basically several levers which a gambler can pull, and with each lever giving a different return, right? And the probability distribution for the reward corresponding to each lever is different, and it's unknown to the gambler. So the goal is to maximize our overall profit, and to do that, we're trying to find the most profitable bandit. So we're not, as you may get confused by this image. So this crazy octopus is trying to pull all these levers together, but the thing is, you pull them one by one. And you basically collect information and then decide which machine is the best one. So let's say this is the best one. So then you continue pulling this lever, and you get collect more and more rewards. So formally, a multi-armed bandit is a tuple, basically, of A and R. A is a set of actions or levers. So you pull the levers. And R is an unknown probability distribution over rewards, right? So you do actions, you get a reward, and there's a probability distribution for each one of them. And the process is simple, as I mentioned. At each step T, the agent selects an action, pull a lever, and the environment generates a reward. And the goal is to maximize the sum of our rewards, right? So this is our kind of first definition. There's really nothing. It might seem a little. This slide might seem a little mathy, but it's in fact very easy to understand. Sadia asked, "How can we add noise to greedy policy?" Sadia, I will explain that in our class, in our practical, right? But it's in fact very simple. So you know that we define the action value Q as this. It's basically sum of the rewards when we take action A in time prior to time T, and we divide it by the number of times A has taken prior to T. And to simplify this notation, we concentrate on just one simple action, or one single lever, right? So let's Q sub n denote the estimate of its action value after it had been selected n minus times. So we're saying that, all right, so here's all the reward we got by pulling this lever, and this is the number of times we do that. So this is an average, right? This is just a simple average. And that's the value, that's how we define it. That's the value of that lever. You kind of do this action again and again, all of them, and then average them. And so the higher is kind of the better. And we can do some more algebra, and we turn this definition into an incremental one. And as you can see, we kind of extract the last reward from it and multiply some numbers here. And we kind of juggle around some of the expressions. And in the end, we have this. So Q, the next value for, if you want to update this, you kind of gather one more reward, subtract it from what we had. And this is going to be our error we added to our previous value. And this is kind of the general pattern for almost all machine learning or learning algorithms. We have an estimate, an old estimate, right? We observe something from the world. Maybe it's a label in supervised learning. It's a target in reinforcement learning. You subtract it from our old estimate. This will give us an error. And this error with a step size can update our old estimate, which can give us a new estimate. And if we do this iteratively enough, it will update our algorithm. Now consider some technical difficulties here. Now consider the 10-armed test bed. I'm going to show you something that will demonstrate this. So this is basically the way you can update it with the epsilon greedy algorithm. So you're looping forever, and you're updating Q based on the value you're collecting. And this is the formula that we derived in our previous slide. So this epsilon greedy can iteratively find the optimal action or lever. So let me share my screen. So this is a representation of an kind of multi-armed bandit. As you can see, we have 10 slot machines here, and the true means are here. These are all normal distributions. You can hide it, so there's no cheating, but just for the sake of this representation, I'm going to show them. So these are the true values. You can reset it to other values, and as you can see, this is the best one. This is the one that we want our agent to find. So if I set my epsilon to 0 and I start it, so not in this case, yeah, all right, so this is probably the best one. Let's do the exploration again. So you can see that epsilon is 0, so it finds the best thing it observes first and then stick to it forever. And this is not good. We don't want this. If I add just a little bit of epsilon, you can see that it starts exploring and eventually finds this. But the thing is, it's kind of too late, and it's already explored so many other irrelevant things. So one thing that we can do, and we're going to do in our algorithms, is that we set it to the highest possible. So it starts with the radical possible exploration, and then we start decaying this to lower values. So in that way, little by little, it starts to act more and more greedily until we may even decide to completely collapse it to 0. So it's going to just exploit in the end. But that's kind of the far end of our learning process when we explore enough. So let me add more and more machines. Let's say 200 machines. So again, the problem we have with just one, it sticks to the first best thing it finds, or I can start from a very radical number and then little by little decay it. So you can see that it finds the best one and stays there forever. And it's kind of, this is the thing that we're maximizing. Guys, can you see my screen now?
No. Yeah.
Right. All right.
Yeah.
All right, thanks. And so as you can see in this process, for instance, when epsilon was set to 0.1, it got to a better, but these are not decaying epsilons, these are fixed epsilons. And as you can see, 0.1 found the optimal value much faster than greedy, which was stuck, and this one, which wasn't exploring enough. All right, so one thing that I want to point out is that you see this thing here, right? So this is the multi-armed bandit problem, and these are the distributions of each lever in this setting. Now, the reason we are interested in multi-armed bandit problem is that in reinforcement learning situations, in reinforcement learning algorithms, each state is like one of these multi-armed bandit problems. So in each state, we have multiple actions to do, and we don't know which one is the best. So we use similar idea in all of them to update and eventually find the best action in that particular state. So that was kind of the message of the multi-armed bandit problem and how exploration is relevant in finding that. So given that, let's define two more things, trajectory and return. The life of an agent, even it can be an artificial one, or in reinforcement learning, or even an organism, can be formally captured by a sequence of states, actions, and rewards. And so we start from one state, we do something, we get a reward, we go to the next state, and we do something, and this continues until we reach the terminal state. And it's basically a sequence, and you can save it in a list or array and then use it later. So that's why it's relevant and important. And we use that to define our return. So the return is the thing that we are trying to optimize, right? So remember that the goal of reinforcement learning is to optimize cumulative total reward. And return, or G of t, is a total discounted reward from time step t. So in each state, the return is when you add all the rewards you will get in the future by being in that particular state. And we tend to discount these rewards, and there are many reasons for that. There are mathematical reasons. There are psychological reasons for that. So for instance, mathematically, it's convenient to discount rewards because it adds to a finite number, and of course it avoids infinite returns. And there are also biological reasons for that. So for instance, living organisms prefer immediate rewards than later rewards. Yeah, so if you set this gamma to 0, it means that it's absolute hedonism. Your agent is just trying to maximize the most immediate reward. If you set it, you have to avoid extreme versions. If you set it to 1, it means that it's considering all the rewards similarly, which is not very beneficial for the agent in playing optimally. Yeah, so this is one of the things. If all the rewards are 1, then you can see that it's just a series and it adds to this number, and that's the kind of the appealing part, the mathematical part of this discounting process. The other thing is that you can turn it into a recursive expression. So you can just factor gamma, and this thing itself is the next return. So G of t is just adding what we got plus the return we're gonna get. So this process will lead to bootstrapping, which we'll use in some reinforcement learning algorithms such as SARSA and Q-learning. So Markup decision process is the mathematical model for reinforcement learning, and we're going to use all the things that we introduced before to basically construct the theory of reinforcement learning. It basically introduces assumptions to deal with reinforcement learning at the mathematical level. There are certain assumptions. One of them is called Markov property. So in a Markov property, we say, and most of these assumptions are kind of loosened up or suspended in practice, but we define it this way. The future is independent of the past given the present. And so in other words, all you need to know is right here and right now, and enough for making decisions. Or probability, in probability language, it means that the probability of going to the next state is only relying on this state. Or if you consider it, it doesn't matter if you consider prior states or not. And the other thing is environments is fully observable. This is clearly suspended in deep reinforcement learning because we deal with a lot of partially observable environments. But even the notion of approximation itself is kind of dealing with kind of partial observability. And almost all reinforcement learning problems can be formalized in Markup decision process. So here's the actual thing. So this is Markup, right? So it's basically a tuple. Whenever you're formalizing a problem in reinforcement learning, you have to gather these information in order to update your agent. So one of them is state, which is a finite set of states. The other one is the finite set of actions. There are certain things you can do, and you should know about them. This is usually unknown. We kind of have it for some algorithms, but those algorithms are called model-based. In model-free algorithms, we don't know this, and we're trying to approximate this. It's a state transition probability. So it's just a probability distribution. It says that given that we are in a certain state and we do something, we'll move to this state with this probability, and we will receive this reward with that particular probability. And this is if you know this, it's actually very simple to solve reinforcement learning problems with some algorithms such as dynamic programming, which I'm not going to cover today. But again, I think the most interesting part of reinforcement learning is that you don't know this, and you have to do it with your algorithms. The other one is reward. So it's a function, an expectation over rewards you will receive. If you were in state S, you did action A, and you move to S prime, it means that it's you're expecting to receive a certain amount of reward. And also a discount factor, which we discussed. It's basically the value of future rewards for our agent. So I think you saw this on iLearn in time loop movies, such as Groundhog Day, or a recent one like Boss Level. The protagonist is stuck in a time loop, and they have to learn enough to accomplish something to break the loop. And training a reinforcement learning agent is very much like this. This is basically a kind of executed version of Markov decision process. So you see in the beginning of the movie, like the algorithm, we start iterating through episodes. Each episode starts more or less from the same place in the movie, and this is where we reset the environment. We also have to reset the agent, like this, and or the protagonist to the same state as well. And just note that resetting the agent doesn't necessarily mean wiping its memory; it just means setting it to the right state. And then the agent, like the actor, has a limited time, like capital T, to finish the episode. And in each time step, the agent in reinforcement learning and the protagonist in the movie is presented with a particular state, like this, and which it has to act upon. And the action influences the environment, may or may not guarantee a reward, but most certainly changes the state of the world or the environment, and the agent sees all of this and learns from them. Hopefully, it learns from all of those. And the other thing is that if it dies, or I don't know, it ends sooner than the maximum time step, we need to break the episode and go to the next one. So that's kind of a fun way of relating to Markov decision process and learn how we actually train our agent. What is a policy? A policy shows up in different parts of artificial intelligence. One of them is reinforcement learning, of course. The other one, you also see the notion of policy in automated planning. But a policy is basically a function that maps the current state onto a set of probabilities for taking each action, also a distribution over A given S, right? And one thing that you should notice that in automated planning is usually deterministic, but it's evident that deterministic policy is just a special case of stochastic policy when the probability of one action is 1 and the other one is 0, right? And so the solution, this is kind of the most important thing. and the holy grails of reinforcement learning. The solution to an MDP is a policy. This is what we're trying to find that associates a decision with every state that the agent might reach. So an optimal policy is something that we strive for. Now, what is exactly a value function or a table of values in this example today, tabular methods? So if you provide a policy, value functions can predict the reward in the future of that policy, and a policy can be derived from it. So I guess a good example, a good analogy for a value function is like an advisor. It doesn't really tell you what to do, but it presents you with the value of each action in certain state. And well, it is obvious that given having a good advice, you can make the optimal action, and you can derive an optimal policy from that. So that's kind of the value function. And in kind of value-based methods, which we're going to discuss today, there are also policy-based method. I'll talk about the distinction later in further slides. The value method is like a proxy. It's a proxy for a policy. We can't find the policy. Well, when we can't find the policy directly, we try to optimize the value function and then derive policy from that. So we have two popular value functions. A state value function, V of the Markup decision process, is the expected return starting from state S and then following policy pi. So it means that it's just telling you, in a very casual way, if you give it a state, it will let you know the value of that state, right? So it says, well, in general, if you're in this state, it means that you're going to receive this amount of reward no matter what you're going to do, right? And probably a more helpful value function is the Q function, which is action value. And it just tells you that if you are in this state and you do this action, you will likely to receive this amount of reward or return. And that's basically what it means. So these are some math about how you can basically turn this thing. So this G itself, you remember that we said that G of T can be recursively written as R sub T plus 1 plus gamma G T plus 1, right? And these are all used to derive better, kind of more recursive definitions of value functions. And this thing is called bootstrapping, and we use that in SARSA and Q-learning algorithms. The proof is not really important. I just provided because I thought if you're kind of interested in a rigorous proof, you may want to explore that further, but it's not really important. And the thing is, you can decompose the value functions, either Q or V, to immediate reward plus the discounted value of successor states. And we also have the Bellman optimality equation, which is basically maximizing these things, and this maximizing kind of function will go inside them. Again, I'll talk about them later. I just thought that I should add them here. If you get confused later, you can go back and look at them. All right. In this slide, we can mathematically prove this thing, that if a value of a policy is larger than the other one in all the states, it means that the policy is better than the other one. But the bottom line is that by maximizing a value function such as V or Q, you can optimize its corresponding policy. That's the bottom line of this. And that's the reason why we are optimizing these value functions, because we know that if we find a better value function, we can find a better policy and hence, guiding our agents better. Yeah, that's the thing. And I know that our focus today is mostly on Q function, not V function. Q function is the one that we can derive a policy directly from it. All right, before going any further, let me talk about some important concepts. So you saw that I talked about value-based and policy-based methods. And here we have two more, model-based and this weird thing, actor-critic. Don't worry about them so much. It's not that important. I just wanted you to see the big picture of the entire reinforcement learning. So in model-based, the algorithm is required to have or will generate a model of the world for successful execution. It's like the way we learn things, right? So when you learn something, when you explore an environment, you create a mental model of that thing. And sometimes you can use that mental model to kind of relive that experience. So this is pretty much like in model-based algorithms. They're not that popular and they're not that successful, but the notion is this, that basically your agent tries to create a model of the world and use that for its kind of retrospect training. The value-based, which is very popular, is the methods that use they're model-free. They don't have the probability distribution, the transition probability, and they first update the value of the state action iteratively, and then use those values to approximate optimal policy, as I mentioned. So key-learning, SARSA, and the DQN on week 12 are part of that. Policy-based is specifically the topic of our week 12, or sometimes they call it policy search. So they kind of bypass the value function, and they directly connect states to actions, and we give states to neural network, and it tells us the desirable action. And so reinforce and PPO are one of them. I will implement reinforce on week 12, but maybe not PPO. Actor-critic is very interesting. In fact, there are some evidence that the brain is operating based on actor-critic methods. There are basically two neural networks working together in learning the task. One is generating the action, the policy. The other one is basically nagging to the other and kind of saying that this is a critic, right? This is informing the other one about the quality of the action generated. And they kind of struggle with each other until they both learn the optimal action and the optimal evaluation. It's a very interesting topic. We'll talk about this on week 12. And the other notion is the on-policy and off-policy algorithms. So the distinguishing feature of on-policy and method is that they estimate the value of policy while using it for control. It's like the on-the-job training. So when you're doing something and you're learning from that while you're doing it, is like on policy, right? You're following what you're doing, but you're also learning from what you're experiencing. Now, the off policy is when you're updating your policy based on other sources. So, for instance, attending a class can be an off policy algorithm. You're not updating your understanding of something, not just based on your experience, but you're gathering information from other sources and updating yourself. And of course, this is more data efficient, but in practice, this one is more effective. And I guess humans kind of balance these two. And when we're learning, we kind of mix them and we use our own experiences. And also, we reappropriate others' experiences for our learning. And this is clearly a good way of asynchronous, using it for asynchronous architectures, meaning that we can collect data from multiple concurrent behaviors. And this makes it very interesting for imitation learning and other approaches. All right, so let's talk about our first algorithm here today, the Monte Carlo algorithm. So the Monte Carlo is the name for any random method that approximates something just merely by sampling data from it. I'm going to show you an example for that today. So the method dates back to the 1940s and the Manhattan Project when they were developing the atomic bomb. I think a physicist, I forgot his name, but he developed this for the statistical approaches to, I guess, quantum mechanics or something like that. Anyway, and so in reinforcement learning, a Monte Carlo method does rollouts, which is usually a jargon, a fancy name for running the environment or game for one or few episodes. And the reason for this is that the algorithm doesn't have access to the dynamic of the environment, as you saw in the model-free algorithms. So the transition probability in Markup decision, process model, and it needs to be approximated by sampling. Now, to show you the power of sampling, let me show you a geometrical representation of using Monte Carlo in approximating the mathematical constant pi. So I'm gonna share my, let me stop this again. So guys, can you see my screen?
Yeah.
All right. So notice that, guys, I can see that there's some questions. I'll try to answer them when we're finished. All right. But you keep asking your questions, please. I'll come back, come back to them later. So in this example, we're trying to approximate pi, and notice that we are just uniformly sampling data from this space, and so this is clearly R is 1, and the area of circle over the area of square can be written like this, and when it's 1, it doesn't matter if it's 1 or not, but this division result is pi over 4. So we're basically uniformly sampling data from this area, and we're dividing the number, we're just basically counting all the numbers that are in this area by the entire thing. And if we do that, we get this number. So if we multiply that by 4, we'll get an approximation for pi. So notice that this is just, there's no really intelligence involved. It's just the power of sampling. And Monte Carlo became more and more important as we develop computers and and we have gained access to tremendous amount of computational power. Before these kind of samplings were not really possible. So yeah, this is just basically the computational part. And this is the way I'm calculating it. You see that if the x squared plus y squared is less than or equal to 1, then I'm counting it, and then I'm going to divide it by the number of samples. So let's see. So you can see that I'm testing with 10 samples, 100, 500, 1,000, 2,000, and so on to 5 million. And you can see how pi is evolving here. So in 100, it's 3 point something. As you can see, it's getting closer and closer to 3.14 and other stuff. I think that the final one is the most accurate. But you can continue doing that, and as we add more and more samples, we can get closer and closer to the number pi. So that's basically what we do in Monte Carlo algorithms. We sample from environments, and we guess which sequence of actions and states can give us the maximum reward. And by the way, this notebook is on iLearn. You can download it and test it yourself. So this whole thing means that Monte Carlo is model-free, and it approximates the model by data sampling and averaging. And the problem of Monte Carlo in reinforcement learning is that it requires to sample the entire episode. This is one of the biggest problems. It needs to sample the entire episode before updating the Q function, and also, of course, its policy. And it makes it not a good candidate for very long episode environments or continuous environments. Also, no bootstrapping involved, which we'll talk about later. All right, so the goal of the agent is to approximate the return, right? The sum of all the future rewards in each state and action. So you see that the agent plays a bunch of episodes with epsilon-based policy. It's either epsilon greedy or epsilon soft, doesn't matter what we call it. It's basically the same thing. And so we have a trajectory of states, actions, and rewards, right? So when the episode is over, we set a value such as g to 0, and we go backwards, right? So we go backwards in the sequence, and we calculate the return for each state and action. And notice that initially, of course, it's 0, and then you add the final reward, which is our probably sub t minus 1. And then, so this is going to be the reward for that particular state. And the next one is r t minus 2 plus gamma g t minus 1, which was this value. And you can see we're little by little constructing the return for each state and action. And we gather them, and in each iteration, we're updating our Q value, which will be more obvious from the next slide. So this is the actual algorithm. We don't need this. This is not part of this algorithm exactly. So we have, and also not pi, because we're not using epsilon soft. We're using epsilon greedy here. So we initialize the Q arbitrarily, usually by 0 values. It's basically a table of values, right? And S and A, so S is rows, and our columns are actions. So Q, S, and A is like one cell in this table. So after generating this, so again, learning happens only in hindsight. So we play the entire episode, then we look back and update our Q function, which leads to a better policy for the next iteration. And that's pretty much the essence of this on-policy first visit Monte Carlo algorithm. Now, this is a first visit algorithm. There's nothing really cryptic about it. It just means that we keep a record of all the state and action pairs we visited before, and we updated them in a backward sense. And if we kind of saw them, we don't update that state and action anymore. We will suspend this in our practical, and you will see the influence it on the algorithm itself. Now, in each step of the update process, we get the return G of the state associated with one particular state and action, and this return is some sort of ground truth. So this G is like a ground truth or a sample from the environment, which helps us to know how far our approximation was. So this was our original approximation, and this creates this error thing. This error that you saw that we have an error, and this is the step, our learning rate, and then we update our older approximation. We get to a new value for our approximation of Q, S, and A, and yeah, that's pretty much it. Again, this part is not relevant. It's part of the epsilon soft algorithm. We're using epsilon greedy. You don't have to know this. I'm just adding it because it was part of the original algorithm of the book Sutton. So this slide is not that important again. I just added it to justify why I proposed that epsilon soft policy that was mentioned in the algorithm and the epsilon greedy are similar. Just notice something, no matter which one we use, epsilon soft or epsilon greedy, either epsilon, so in each state, the best action has the chance of 1 minus epsilon. So in this image, you can see that the best action has the chance of 1 minus 1 minus epsilon plus epsilon over the number of actions to be chosen, and the rest each has just the epsilon over the number of actions. And the reason is that optimal action has the equal chance of being chosen in the random process as well. And this means that if epsilon is small, our policy becomes more and more greedy, right? So again, you don't need to worry about these probabilities. These are all kind of done automatically by epsilon greedy. When you implement epsilon greedy, that's pretty much the entire the probability of each action in that setting. All right. So temporal difference algorithm, SARSA and Q-learning. So now we saw that Monte Carlo can be used to update the Q function and eventually the policy of an agent. but it suffers from delay in update. And the fact that we need to wait till the end of the episode is honestly a big issue in updating our algorithm. So bootstrapping has its origin in, I guess, in early, the word bootstrapping in early 19th century with the expression of pulling up by one's own bootstrap, which is obviously impossible. But later it became a metaphor for achieving success with no outside assistance, right? So the Bellman, the Bellman, this guy here, the Bellman expectation equation simply means that instead of waiting for all the rewards to show up like Monte Carlo, we can just approximate our Q value in a state and action just by adding the reward, right? Just by adding the reward, the immediate reward you got, and our current understanding of the next state and action Q value, right? And this idea is the basis of Sarsa algorithm. Now, the Bellman optimality equation, which is this one, and it uses it for, basically we use this for updating our Q-learning algorithm. And it's saying that we consider the next state, the next reward, but we just assume that we're going to follow the optimal action after that. I'll explain this further when we're discussing Q-learning. Don't worry about it. And you will have a chance to implement it directly in your practical, so you'll understand everything about this. And again, these are just mathematical stuff. So just one thing, notice that these are expectations, right? So sometimes these things weird people out. So when you're calculating an expectation, you know that you're in mathematically, it's P of X times X, right? So it's basically averaging over all the values. But we don't do this directly because we don't have access to this in most algorithms. So we do sampling, right? So sampling is the equivalent of calculating these things directly. In dynamic programming, again, which I excluded it from this, and it's like the grandfather of reinforcement learning. We do this because we have access to this probability, this transition probability, but not in model-free reinforcement learning algorithms such as Sarsa and Q-learning. So Monte Carlo has a low performance, right? And due to its high, and of course it's we updated very, very late, but it has a low performance due to its high variability. And so you know that we have this tension in machine learning called bias and variance trade-off or dilemma. It's usually either one. You can't have both. If you increase variability, you decrease bias, and vice versa. Now, this variability in Monte Carlo is due to the fact that we're relying only on rewards we got from our environment, which are samples with a lot of noise, right? So when we add bias to it by bootstrapping, right? So it's biased because it's based on our prediction. What we're doing is that we're stabilizing it based on our current approximation. Our approximation is approximation is like our line in regression, right? So it's very stable compared to the data that is very noisy and it's all around the plane. And so at first it's going to be very inaccurate because of course our Q function is not right. By little, it gets better and better. And in fact, TD methods such as Sarsa and Q-learning are generally better than Monte Carlo methods and also easier to implement. And this is how it's done in Sarsa. So the agent takes one step in time step t, let's say such as this, right? And it observes, so it takes one step, it observes the next state and its reward, right? So a reward and a state. And it chooses the next action, right? Without taking it, but it decides what to do next, right? And this gives us the equivalence of the return or G in Monte Carlo, and the difference between this value and our current approximate Q of S sub t and A sub t creates an error, which we can use to update our current approximation of Q value. So this thing, right? So this was in Monte Carlo, this was G of t, right? Our return. but we don't have the return here. We just have one reward, and we approximate the rest of it with our current value. But again, mathematically, this is like the return. And this thing here will be the error, or the error we had in our updating, and we use that to update our Q value and get to a new value for our Q. And so this error term is also called the temporal difference, or TD error, and hence the name, TD methods. And so alpha here, is our learning rate, and in most tabular cases we set it to a fixed value, such as 0.1 or something. You can also optimize it by testing different values, but it's usually like that. In deep reinforcement learning or approximate methods, we use much smaller values, because basically in those cases we're updating a neural network, and it should be smaller. Yeah, so this is the algorithm. Notice that SARSA, unlike Monte Carlo, is incremental, and we update it in every time step. And this incremental property also helps us to its faster convergence, and makes it a possible candidate for continuous environments or episodic environments with very long episodes. So I think this is pretty much like the MDP loop. If you understood that, it's very obvious how it's done. In each episode, we initialize, so this is the first state. And then we choose our action based on epsilon greedy. So when we go inside the episode loop, we take that action, observes our reward, and the next state, we also remember that we have to choose our next action, because we need to update it using this formula. And then we update it. We need to replace them with old state and action. And this continues until the episode is over, and this continues until the agent learns how to do that. And that's pretty much it. That's the entire algorithm. I don't know the feeling about this, but I think it's very easy to implement such a thing, at least algorithmically. There's nothing really cryptic about this. So, and we have an error based on we observed, and we bootstrapped, and we update our Q function again and again until we get to the final thing. And interestingly, this is a very effective algorithm. Now, the other thing is Q-learning. Q-learning, as you can see, is strikingly similar to SARSA, and in fact, it's sometimes called greedy SARSA. The only difference is that you don't need to choose the action in the next, state to approximate it, and we simply assume that we're going to follow the greedy action after the current state. You notice that we don't have a prime action here. So we just take, we choose an action for the state we are in, derived from Q using epsilon greedy. And we take that action, we observe our next state and reward. And we are just in our next state, we're using the maximum Q value, which means that you're assuming that you're following the optimal action after where we are now. Now, to sum up, SARSA is on policy. Again, it's just learning from the policy that it's following, and it learns the Q values that answer this question. What would this action be worth in this state, assuming I stick to my policy, right? I think it's very clear what that means, because it's following, it will follow its policy for updating its value. Now, as you can see, we're kind of committed to use our Q values in choosing the next action as well. Now, this commitment makes SARSA on policy again, meaning that it only learns from itself. But it's not the case in Q learning, which makes it off policy. And the question it's answering is that here, what would this action be worth in this case, assuming that I stop using whatever policy I'm using now, right? And start acting according to a policy that chooses the best action according to my estimate. So it's not completely irrelevant to our current policy, but it's kind of saying that, let's say I'm following the best of myself from now on. and that's how it's updating itself. And interestingly, Q-learning in many cases, it's fast converging, but I guess the SARSA is, it tends to be more, I guess, conservative. It's not finding the most optimal policy, but sometimes the safest policy, which you will see in some examples. If you look at Sutton's book, there's an example about edge walking that Q-learning will go to the edge because that's the optimal policy, but SARSA distance itself from that edge because it's safer to be there. So that's how they operate. Now, so those are the algorithms that I want to cover. So you can see that algorithmically they're not that complex, and the only thing is that there's a table of values there in Q-learning, SARSA, and Monte Carlo, and we're going to train them for 2 block world environments. These are clearly not suitable for more complex methods. For those for more complex environments, for those things we need approximate methods and deep reinforcement learning methods, which we will cover on week 12. Now, this is my kind of final slide. And the question is why video games are good for platforms for RL. So first of all, the first point is that they're cheap, right? Compared to robotics. It's much, much cheaper. You don't have to construct anything fancy. You don't need a $1 million budget to do that. It is accessible, right? That's another thing. It's kind of related to cheap, being cheap. That you don't need to be, for instance, in Boston Dynamics to use it. You can just write something or download something and use it. It's parallelizable, so we can easily spawn multiple parallel environments. And they're easy to modify because it's just basically code, and you can go and modify your code and create multiple environments from that. It is also beneficial for the video game industry, especially in, for instance, for designing NPCs. And you know that NPCs or non-player characters are notorious for being dumb to the extent that it's become a meme and sometimes an abusive language among some gamers as a reference to people who don't think or act in a very awkward way. Now, this problem is mostly because of the way their behaviors are defined, which is either a hard-coded thing or they obey some heuristic. And in both cases, it's rigid and inauthentic and not very natural. So reinforcement learning can provide a third solution and help the NPCs to come up with a better policy for their actions rather than sticking to one dictated by a heuristic function or something. Now, there are some benchmarks and environments for reinforcement learning. So the one that we're going to use today, and you will see in most papers, is OpenAI Gym. So this game, for instance, this is I forgot its name. Maybe I don't know, Beam Rider or something. Anyway, so this is one of the 60 environments they provided, and sometimes people, to make sure that their algorithms is better than the previous one, they use these methods, they use these environments for testing. There's Majoko, which stands for multi-joint something. And so this guy, this dancing guy, as you can see here, they're just controlling their joints the way we do. So we kind of forget about this, but we kind of develop this ability in our early childhood that acting is not just willing to do that. You have to move the right joints to do it. And this is basically an effort to use reinforcement learning to train these humanoids. And they learn from scratch how to walk, how to stand up, and do things that are kind of relevant to robotics and dynamics like that. The other environment is wisdom. You see that in certain papers. It's a very ancient game, basically from 1990s. People who remember, it was a very interesting game, probably the first, well, the first of its kind in the first-person shooter game, and it's also used to develop some reinforcement learning agents. And the interesting thing about wisdom is that it's based on a partially observable environment, and you can see all your surrounding, just this view which is very limited. You can't see behind your back. So it's also interesting to solve it with reinforcement learning. DeepMind Lab, it's kind of newer. It was developed in 2016 based on the Quake game engine, I guess. And also we have two very popular game engines, which if you had video game lessons before, you're probably familiar with them. One of them is the Unreal game engine, and the other one is Unity by Microsoft. You basically develop games with these things. I mean, these are the real deal. You can just sit down and write a game from scratch with these things. For Unreal, there's a package called MindMaker, Deep Reinforcement Learning Package, and for Unity is ML Agents. So these are also used to develop NPCs and train them. Again, to sum up, reinforcement learning is big and interdisciplinary topic, long history, elegant mathematical core, novel algorithms, a lot of uncharted territories, and endless possibilities. The thing that I think the most is important about reinforcement learning is that it's a unifying thread that pulls the entire AI together. You can basically use anything here: vision, perception, language, acting, planning, learning, even knowledge representation, which is kind of missed out from the rest of machine learning, but you can also bring it here to reinforcement learning. It has the capacity to reduce learning problems to small steps, as you saw today. There are some recent developments that show tremendous capacity of RL in robotics and simulated environments. And the best is yet to come. Week 12, we're going to discuss deep reinforcement learning with a lot of exciting applications in controlling certain agents. Thank you for joining today. That was my lesson. If you have any questions, you can ask.